Okay, stats, chapter 10, we are going to do like this review page today, just to kind of recap chapter 10, and then we're going to do a couple sections from chapter 11 before we start our like end of the year big review packet. You will not have a test over chapter 10, but this chapter 10 review, I will only go through a few of the problems with you, and then the rest you'll have to do on your own for an assignment and turn that in. So just beware as we go through this. I'm not going to make you do any of the really cumbersome, hard, icky calculations from chapter 10. It should be pretty straightforward. You will need to use your computer to plug in some of these like tables, like on 3 and 4. So make sure you have that handy so you can do that. But none of the big icky equations, more like the interpretation of chapter 10, basically. So starting with number 1, I'm going to do number 1 with you, and then I'll have you do number 2, which is kind of similar to it, on your own. So number 1, given the linear correlation coefficient R, they give us the R value right here. And then they tell us that we have a sample of 25, okay? They want us to determine the critical values of R, okay? And use your finding to state whether or not the R that they have for our data is a good enough one. So does that represent a significant linear correlation? Significance level of 0.05. So our fish value is 0.05. And when they ask for the critical value, they're saying like, okay, looking at that chart, which is this guy right here, that you guys should have. Some of you guys have a page that has like 3 of them on it. Looking at that here, like what is considered to be a good R? Our R is 0.543, but is that considered to be good enough? Okay, so R lives between -1 and 1, and we've said that 0 is a bad R, and -1 and 1 are going to be good values of R. Now, if it has a negative slope, it's going to be closer to -1. If it has a positive slope, it's going to be put closer to +1, okay? So that's just telling the slope of it. But we have to decide, like in the middle here, where these cutoff marks are from what's considered bad and good. And that is determined by this table, okay? So if our N is 25 and 0.05 is our significance level, we're going to go here. And notice that this is not degrees of freedom, so you don't subtract one. We're just going to do 25 and 0.05, so we're going down to 0.396, okay? So when it asks for critical values, there's an S on the end of there, 0.396, but it's positive and negative. The positive 0.396 is here, and the negative 0.396 is here, okay? Now, good range is anything above that, or anything below the negative, and bad is considered in between those, okay? So this is our critical value. That's the first thing that we have to answer, and then it says, use your finding to state whether or not the given R is representing a significant linear correlation. So like basically, is this telling me that they are linearly related? Okay, so if R is 0.54, I wouldn't think that 0.54, like that would be a very good R, but evidently because it lives on the good side of 0.396, evidently that tells me that that's good enough. And our N is 25, which means like 25 data points. That's getting up there in number. And typically the more data points you have, the worse your R gets, because it's hard to have all of those data points live on a straight line. So R represents a significant linear correlation. So yes, linear correlation according to what our R is. They are linearly, whatever variables we're comparing are correlated in a linear pattern, because that is above the threshold of what's considered to be good, okay? They're asking you similar questions on number 2, so I'll have you do that one on your own. Number 3, find the value of the linear correlation coefficient R, okay? The paired data below consist of the temperatures on randomly chosen days and the amount a certain kind of plant grew, okay? So, I mean, they're probably going to be correlated. They're recording growth every day. So what I'm guessing is happening is like these higher values of temperature are probably going to represent higher values of growth. Not in all cases, because this one's lower temperature and that had really high growth. So it's not going to fit a linear pattern completely, but you know, it might be correlated. So they want you to find the value of R, okay? And so what you're going to have to do, I'm not going to do this for you, you're going to have to plug these in. Your X's are going to be temperature, your Y's are going to be growth, and plug that in. And on a scatter plot, I think you guys should all know how to do this, on your Google Sheet that you open, type those in, or you can do it on your calculator. Some of you guys know how to do that with your fancy graphing calculators. It will spit out like your y hat equation, which you don't necessarily need for this problem. That's going to ask you, that for number 4. But they want specifically what the r is, okay? And I don't think on Google Sheets it gives you r, it gives you r squared, okay? So you're going to have to take the square root of that number to get your r value, okay? It doesn't necessarily have to like ask us, like it did up above here, if it's considered to be a good r or a bad r. We're just trying to find the value of r, okay? So plug those in, find the value of r, you're done. Number 4, use the given data to find the equation of the regression line. So you're looking for that y hat line. And it's going to be like mx plus b, and I guess your b could be plus or minus, so I'm not going to put plus or minus, because it could be one or the other. But do that, round the final values to 3 significant digits, okay? Yeah, three sig figs, if you can remember what sig figs are, or at least, I don't know, 2 decimal places maybe, or whatever, okay? So plug those in, get an equation. You only have 5 data points. You don't necessarily even have to list the value of r on that one. You can if you want, but there's what you're trying to find for that, okay? All right, next one. Number 5 says the coefficient of determination is what you're trying to find, given that the correlation coefficient, r, is 0.738. R is 0.738, okay? The coefficient of determination, that is r squared, okay? So all you have to do is take that guy and square it. I'll go ahead and do that. Let's see, 0.738 and squared. 0.545-ish. 0.545, okay? Now, we just talked about recently about that coefficient of determination and how this number actually represents a percentage, okay? So if I move that to a percentage, that's 54.5%, which means that 54.5% of my data can be explained by a linear function. Otherwise, the rest of it is just kind of like outliers that are like not really following the linear pattern, which doesn't seem like a very high percentage to me. But again, the more data values you get in there, the more random things are going to happen. So 54% of my data can be explained by a linear pattern, I guess, is what we can conclude with that. But really, the coefficient of determination is just this 0.545, okay? All right, number 6. We'll do this number 6, and then I'll have you do quite a few of them on your own. Based on the scatter plot, select which one is the most likely value of r. We said r lives between -1 and 1, with 0 being the bad one in the middle. Okay, so like the dots would be all over the place if it was a value of 0, okay? But this one, these dots are all on that straight line. Like they're all filled in on that straight line. So I'm going to guess that that value is going to either be really, really, really close to a -1 or really, really, really close to +1, okay? And we choose which one based on the slope. So since this is sloping downhill, I'm going to guess that it's probably going to be close to -1. So I'm going to go with A is the answer for that one, okay? It wouldn't be -0.5 because -0.5 is going to have some data points that are off the line. So it's going to be, not quite. But those ones all look really, really, really perfect on that line. So I'm going to go with -1. Don't choose B. Okay? I'm going to do that. All right, 7. Do this one on your own. Determine which plot shows the strongest linear correlation. So which to you looks like it's the most in a linear pattern. Okay, go with that for number 7. Number 8, you figure that one out. A blank is a point lying far away from the other data points on a scatter plot. I think you might be able to figure that one out. And then 9 is asking kind of the same thing as we just did on number 6. What is the probable value for R in that situation? Okay, so figure those ones out. Number 10, 11, 12, 13. We'll go through some of these. Here we go. Number 10, which of the following statements concerning the linear correlation coefficient are true? So they give us 4 scenarios right here. Okay, and we'll go through each one. 2 of them, it looks like, are, because our choices are A, B, C, and D, it looks like 2 out of the 4 are true. So is it number 3 and number 4 that are true? Is it number 1 and number 2 that are true? I don't know. We're going to find out. Okay. So number 1 says this one right here says if the linear correlation coefficient for two variables is 0. So if r equals 0, then there is no relationship between the variables. Okay, all right. Now, I'm cautious to say that there's no relationship. We know that r goes from -1 to 1, okay? And 0 is a bad linear relationship, but that's bad linear relationship, right? If our r is close to 0, there could still be a relationship between the two variables, but it might be like a quadratic, like a parabolic relationship, where my dots are like following some sort of a parabola, right? It's just saying that it's not a linear or a straight line function, okay? So I'm going to say false on that one, because just because it's 0 doesn't mean that there's no relationship. It's just not a linear relationship, okay? Number 2, if the slope of the regression line is negative, then the correlation coefficient, which is r, is negative. So if slope is going downhill, then the r equals negative. I believe that is true. So number 2 is true. The value of the linear correlation coefficient always lies between -1 and 1. That's the r value, has to lie between -1 and 1. That's true. And a linear correlation coefficient of 0.62 has a stronger linear relationship than that of -0.82. Okay, so 0.62 is going to be on this chart right here, and -0.82 is going to be over here. Now, just because 0.62 is positive doesn't necessarily mean it's better than a negative number. The closer it is to these 2 points means the stronger the relationship. The negative just means that it's going like downhill, okay? So not necessarily true that this one is better, and in fact it's not, because 0.82 is going to be closer to -1. So 0.82 is actually better than 0.62, even though it's negative. So that is false. So which of the following statements concerning the linear correlation coefficient are true? 2 and 3. Which one is that? D. D is 2 and 3. Okay? All right, there we go. All right, number 11. For each of the 200 randomly selected cities, so that means N is 200, Pete recorded the number of churches in the city and the number of homicides in the past decade. So X equals churches. This is going to be a fun example. Y is the number of homicides. Like how many people kill each other. Like that's what that is, okay? He calculated the linear correlation coefficient and was surprised to find a strong positive correlation between the two. Okay, and then it says, does this suggest that building new churches causes an increase in the number of homicides? Well, I sure hope not. Like, that should be the opposite, I would think. But does this suggest that more churches causes more homicides? That's what it's leading you to believe, according to the R. There's a strong linear correlation between the two. And just because they're correlated, let me underline those words. Just because it's correlated, we talked about this before. Correlation does not equal the same as causation, which means that just because they are related to each other does not mean that one causes the other one to happen. Does this suggest that the building new churches? No, does not suggest that. Why do you think that there is a strong positive linear correlation that was obtained? So why are they both increasing at, like when the number of churches goes up, the number of homicides go up? Why would that be a thing? Explain your answer with reference to a lurking variable. So could there be something else going on behind the scenes that is causing both of them to increase? Well, let's talk about population, right? If the population of a town is increasing, they're probably going to have more churches. That's going to go up. And homicides are probably going to go up just because there's more people in that area. So just because they're both increasing doesn't mean that more churches are causing more people to kill each other or whatever. It's probably the population increasing that's, like doing that or whatever to both of those, okay? So population is the lurking variable. If something else comes to your mind, please put it down. I'm interested to see if you think of anything else like that could be a lurking variable. Like, I don't know. I would think population would be the main thing that would cause both of those. But if you have any other suggestions, I'm pretty sure it's not churches that's causing more homicides, but population is probably a lurking variable in that case. Okay. So all of those things that you have to keep in mind as a stats thinker when you get these results Just you have to pay attention to all of the variables, okay? All right, 12 and 13, here we go. A, 0.01, so our fish value, that's our significance level, is being used to test a correlation between two variables. If the linear correlation coefficient R that we have found is 0.591, so that's from our data, okay? That was one of the formulas that we did in section like 10.2, which I'm not going to make you do. That's why they give you the result of that. Why is this doing this? So the result of doing all the calculations is 0.519 or 591 for the R value. And what's considered to be good and not good is this, okay? So plus or minus 0.590. What can you conclude? In other words, is there a strong linear correlation? Okay, so again, that kind of goes back to this number line that goes from -1 to 1. Okay, 0 being in the middle, this is bad, and linear is good over here, and linear is a strong linear over here. Okay, it is considered to be a good value with a significance level of 0.590, which is, well, that's a little bit more than halfway, so we'll go about right there. 0.590 and negative 0.590, okay? Oh man, we're just really hugging the line here. 0.591 is just ever so slightly to the right of that 0.59, okay? So, in other words, is there a strong linear correlation? Yes. Strong, and I'm going to be more specific, I'm going to say strong positive linear correlation. Okay, so if it was a negative correlation, it would be doing that, okay? So what's happening is on our graph, whatever variables we're talking about, as one is going this direction, the other one is going this direction. So we have a line that's doing this, okay? A negative relationship would look like this, meaning as this x variable increases, the y variable is decreasing, okay? So that would be a negative relationship. This is a strong positive, which means as one goes up, the other one goes up, okay? So this one is according to what our threshold is, it's considered to be strong positive, okay? It's right above the border, all right? All right, number 13, I'm going to give you an example that's going to come to my mind for this, and I don't want you to write this one down. I want you to come up with your own, okay? And make sure it doesn't match somebody else's. I'll be checking, okay? Give an example of a pair of variables, so like an x and a y, whose linear correlation is likely to be close to 0. So like they're not related. Like two things that are occurring that are not related to each other, okay? So like something for an x and something for a y that tells you that those two things are not related to each other, okay? So what could we put for two things that are not really related? I don't know. Let's say I'm going to talk about the miles you drive to school. The miles you drive to school. Some of you guys drive a little ways. Some of you guys live in town, so you don't have to drive hardly at all. So the number of miles you drive to school, I'm going to say is my x variable, and the y variable, let's do something completely unrelated. We could do the number of books in your locker. Those things are completely unrelated to each other, okay? Like, it's not necessarily true that if you drive more miles to school, you have more books in your locker, whatever. Like, those two things are completely unrelated. So they would probably have an R value that's close to 0, okay? Or you might get a blip in there that says the R is like 0.1, and we'll give that to you, right? But you should have something that's like completely unrelated. So don't use my example, but give me a pair of variables. So two things that are happening that you can collect data on. Like, it has to be numerical data, like number and number, right? Miles is a number, number of books is a number. They have to be numerical data, so not like eye color or anything like that. Numerical data that are unrelated to each other where the R is 0, okay? So look for those, and that's the end of chapter 10, okay? So tomorrow we'll start. Do I have a project going on? Yeah. I have 2 days worth of comparing some data. And so we'll do one more thing for chapter 10, and then we'll start 2 sections of chapter 11. So there you go. Finish that up and turn that in tomorrow.